In this video, I'll be talking about another application of operational amplifier. Here I'll be talking about operational amplifier as adder. So this operational amplifier can be used to execute a summation. Now, in order to understand this concept, that how we can use operational amplifier as adder, let me draw the circuit for it, and let's start with the operational amplifier. Let's start with the resistors, R1, R2, R3, and let's go with the operational amplifier. This is the positive terminal of the amplifier, and this is the negative terminal of the operational amplifier. And here is the output, V out, and the non-inverting terminal is grounded. And let us assume that we have three resistors, and the value of this resistance is R1, this is R2, and this is R3. And we have the input signal here. Suppose this is VA. For this, the signal is VB, and for this, the signal is VC. Okay, we have to connect a feedback resistance like this, and we'll connect it with the output. So this is RF. All right. So now let's analyze this this operational amplifier, where we want to have output in the form of addition of the signals that are input to the inverting terminal of this operational amplifier. So one thing should be borne in mind, that we got to use the concept of ideal operational amplifier, where the input impedance of the operational amplifier is assumed to be infinite. And let's go with some say, for example, here I have the voltage V1. Here it is, as usual, V2, and here we have V out, and if we assume that the current passing through this resistor is I1, this resistor is I2, and this resistor is I3, and here let us assume the current is IF, and let us assume the current here is IX. And let's talk about this junction. Let's suppose that this junction is the junction P. Now I want to evaluate this this operational amplifier, and I want to calculate the output of this operational amplifier, and that output should be in the form of addition of the input signals. Now to start with, at junction P, we can understand that we can make use of Kirchhoff's current law, and we can say that I1 plus I2 plus I3 is equal to IF plus IX. Very canonical concept, that the currents that are entering a junction is always equal to the currents leaving that junction. Now at this point we can use the concept of infinite input resistance. So here the input uh, impedance of operational amplifier is infinite. So if it is infinite, then we understand that the current that this current Ix in that case must be equal to zero. There will be no flow of current because of infinite input resistance. Now to move on, so what's going to happen to this equation is that let me go that I1 plus I2 plus I3 must be equal to IF. Now coming back to this, now what can I say here is, what is I1? It is VA minus V2. And what's I2? That's VB minus V2. And what's I3? It is VC minus V2. So here, instead of I1, I'm going to use Ohm's law, and that is VA minus V2 by R1 plus VB minus V2 by R2, okay, equals plus VC minus V2 by R3. This equals IF. Now what is IF? IF is it is V2 minus V out by RF. So this is V2 minus V out by RF. I think this is clear. Okay. Now the point is that, see, V1 is grounded. There is no current flowing between V1 and V2. We can say directly that the potential at V1 is equal to the potential at V2, and this is what is called as virtual ground. So in this case here, we can directly say that V2 is V1 is 0, and the point is what? Virtual ground. And this point has been already explained in the previous videos. So here we will have VA upon R1 plus VB upon R2 plus VC upon R3 equals minus V out by RF. Okay, so this is my equation. So from here I can calculate the output. Now what is the output? That is RF times it is VA, it is minus here, okay, minus RF times VA upon R1 plus VB upon R2 plus VC upon R3. This is the case. Okay, now to generalize it, let us assume that the resistances that we are using, R1 is equal to R2 is equal to R3 is equal to RF. So in that case I will get the output, and that output is minus times, and there will be cancellations. R1 and RF will cancel, this R and R will cancel, this R and R will cancel, and we'll be left with VA plus VB plus VC. Now why we are getting negative here is a consequence of using inverting terminal of the operational amplifier. That must be clear. So from this equation it's quite clear that this operational amplifier can be used as an adder. We can add the signals so that the output voltage that we obtain is the summation of these the voltages of these signals, and this thing can be extended to n number of inputs that we have talked about in the previous case. Now if I go back to this equation, say for example this equation, and if I take a situation where I assume that this RF is Uh, this RF is R by 3, and then R1 equals R2 is equal to R3 equals R. Now, if I use this condition, let us see what will be the outcome of this assumption in this equation. So in this case, the output will be it is minus, this is R upon 3 times VA by R plus VB by R plus VC by R. And we can understand that V out in this case is coming out to be, these R's are going out, so it will be VA plus VB plus VC upon 3. Now here we can see that this operational amplifier can be used to calculate the average of the input signals. So here we can understand that the output is the average of the inputs that have been used here in this case. So if we have n number of such kinds of inputs, we can calculate the average, and that average will be minus times VA plus VB plus so on so forth Vn upon n. So we have seen two important applications here when we make use of operational amplifier and connecting the input signals to the inverting end of the operational amplifier. One is that we can add up the magnitudes of the signals, and we can calculate the average of the magnitude of the signals that are subjected to the input of this operational amplifier. And the next important thing is this negative sign is because of subjecting our input to the inverting end of the operational amplifier.